So when we said the word antiderivatives, we really meant it. The antiderivative, or the indefinite integral of a function, is really an expression that reverses the process of differentiation. For example, when we found that the derivative of a constant was equal to 0, well, then the integral, the antiderivative of 0 dx, should be equal to the constant. If we took the derivative of a constant times x, we would just get that constant k. So it should be the case that the antiderivative of k times nothing, right? The antiderivative of k should be k times x, well, plus a constant. For any function, here's another rule that we want to know. For any function, if we take a constant times that function, it will be same thing as the constant times its derivative. So in reversing the process, if we want to find the antiderivative of a constant times a function, it'll be the same as the constant times the antiderivative of the function itself. In other words, that constant would get multiplied out. We had a sum or difference rule for derivatives, which said that this derivative of a sum or difference of two functions, f and g, would be the sum and difference of their derivatives separately. Well, likewise, the antiderivative of a sum or difference of two functions, f and g, will be equal to the sum or difference of their antiderivatives. Here's one that we've already encountered. We talked about this. Our rule for powers, x to the n, its derivative was nx to the n minus 1. So the counterpart rule in the rule of antiderivatives is that the antiderivative of x to the nth power would be x to the n plus 1 over n plus 1 plus a constant, as long as that exponent is not negative 1. And we can work our way down the list. We recall all of our derivatives, sine, cosine, tangent, secant, and so on down the list. And we would find that, for example, the antiderivative of cosine of x would be positive sine of x, and that the antiderivative of sine of x would have to be negative cosine of x, therefore. In any case, once we recognize a lot of these rules right here, we can always refer back to these rules, these derivative rules, for our antiderivatives. And the trick is just trying to find a way to make sure that we understand what these rules say. So let's try one now here where we do that. Let's say that I have a function like the one we see right here, the antiderivative of 1 over 4x squared dx. Well, we might not recognize it right away, but we could say something like this. It would be the same thing as the antiderivative of 1/4 times x to the negative second power dx. And so if we write our rule using the constant multiple rule, right, the antiderivative of a constant times a function dx is going to be equal to the constant, in this case 1/4, times the antiderivative of x to the negative second power dx. Now we can employ our power rule right here, which is going to state that we're going to take 1/4, our constant, times 1 over our exponent, negative 2 plus 1. Remember, this always worked as long as the exponent was at negative 1 itself, raised to the negative 2 plus 1 power. And to the end of that, we're going to add a constant of integration. Well, working this through right here, negative 2 plus 1 is negative 1, so we end up with negative 1/4 times x to the negative first plus our constant. Or rewriting the expression back into the form that we started out with, we could say that we have negative 1 over 4x plus our constant. And this would be the antiderivative. Even if the function's a little bit more complex looking, these rules would still apply. Let's consider this one, the antiderivative of the cube root of x minus 2 over the cube root of x squared. Let's look at what's going to happen right here. First things first, let's rewrite this into that exponential form that we like. We will have the integral, the antiderivative, the indefinite integral of x to the 1/3 power minus 2 times, and in this case it's going to be x to the negative 2/3 power if we rewrite that in exponential form, dx. And if we use our sum and difference rule for these two different functions and this constant, this is like saying we want to find the antiderivative of x to the 1/3 dx minus 2 times the antiderivative of x to the negative 2/3 dx. All right, so let's use our power rules right here. This is going to be 1 over 1/3 plus 1 times x to the 1/3 plus 1 power minus 2 times, and we're going to work our antiderivative right here. It'll be 1 over negative 2/3 plus 1, and that'll be multiplied by x to the negative 2/3 plus 1. All of that plus a constant. Notice we're only adding one constant of integration. We could make a constant of integration for each term separately, but in the end they're all going to add up and create one single constant at the end. So all we really need to do is just simplify our expression. Well, 1/3 plus 1 is 4/3, and so when we take 1 over that, we're going to get 3/4, and it will be multiplied by x to the 4/3 power. When we take 1 over negative 2/3 plus 1, that's 1 over 1/3, which is 3, so we're going to end up with 6 times x to the positive 1/3 power plus a constant. And so rewriting this back into the original form that we started out with, our real expression is going to look like 3/4 times the cube root of x to the 4th minus 6 times the cube root of x plus a constant.